Thank you all for joining today's webinar presentation. I'm just looking at the sign-ons here. It looks like there's some people still logging on, so we'll give a minute or two for them to work through any technical issues that they may have and allow them to sign on. So thank you for your patience, and we'll begin the webinar here momentarily. Okay, everyone, we're going to get started with our webinar. I'd like to welcome you to our webinar, Enhancing and Expanding Wastewater Treatment at Pulp and Paper Mills. My name is TJ Willits, and I'll be your moderator for today's presentation. Just some housekeeping items. Obviously, you should be hearing me speak now. There's two audio options. You could either log on through a phone by dialing in and using a PIN, or you could use the computer audio on the panel, as you can see on the right-hand side. Just want to let everyone know that this session is being recorded, and attendees will receive a copy of this recording in about a day or so from an email. So be on the lookout for that tomorrow. On the right-hand screen, you have a question panels. We're going to hopefully have some time at the end of the presentations for a question and answer session with our panelists. So feel free to, throughout the presentation, to go ahead and fill in your question on that panel, and we'll collect them and hopefully get through as many as possible during the live session here today. Right after the webinar, there'll be an opportunity to take a short survey. This helps us to design content that's relevant to you. So we want to make this the best technical presentation as possible going forward. And so if you put your feedback there, there's a place for future topics that you might want to learn about, as well as any other feedback you're welcome to provide. You may or may not heard of Veolia, but I wanted to give a few introduction slides about what we do. Veolia is the leading environmental company. We focus our efforts on three key pillars, and that's water, which we're going to hear a lot more about today, waste, and also energy. Specifically for the Pulp and Paper Company, we have a very wide range of capabilities within water evaporation and wastewater. We handle everything from influent water treatment to utility water, as well as some specialty technology applications such as black liquor concentration, precipitator ash treatment. Of course, we're here to talk about wastewater, but also some overall topics such as water footprint reduction, and then some specialty emergency mobile water treatment capabilities as well. Globally, Veolia has worked with the leading pulp and paper companies across the world here. You can see some of our customers listed here on the page. And we've done a ton of applications, worked with a ton of different types of manufacturers, and you can see where some of our references are globally. We've had experience with, of course, the leading pulp and paper companies, but also we've been working with them as they transition into the future of what this pulp and paper industry looks like. We do this using a very deep portfolio. We have about 350 technologies that we utilize for our business. And here's some of those technologies listed there that are most applicable to the pulp and paper industry. And we're going to talk about a couple of these key technologies throughout the presentation as well. And before we get into our presentation, I just want to let everyone know that we're hoping to make this a webinar content series. And we already have our next webinar scheduled. It's going to be on optimizing kraft pulping and recovery cycle operations. And it's going to help pulp and paper mills learn to be more productive at concentrating their black liquor and removing some of their non-process elements at their facilities. And that's scheduled for Tuesday, October 15th at 2 p.m. Eastern Time. There's a short link on the screen. We'll have that up a little bit later in the webinar for you if you want to go ahead and register for that upcoming webinar in October. And you could obviously email me if you have any questions about this or any future webinar topics. Okay, now we're going to transition to today's presentation. We have with us two technologists. Our first presenter for today will be Rob Franken. He's the Senior Director of Business Development at Veolia Water Technologies. He's based in the Philadelphia office. He has more than 30 years experience in biological wastewater treatment. And at his current role, he works with a variety of industries to help them manage their wastewater challenges through the application of Veolia's extensive biological product line, including anaerobic, aerobic, anaerobic MBR, and of course MBR as well. And prior to this role in the US, he was the managing director of Biothane, which is Veolia's Anaerobic Technology Center. Also with us today is Thomas Philander. He is the Chief Visionary Officer for Veolia's Annex Columnist Group. It's the technology group focused on MBBR. He is based in Sweden, and he's the Associate Professor in Biotechnology at Lund University. He started his R&D work on biological treatment of pulp and paper industry effluents in 1982, wrote his PhD thesis on the subject, and founded the company Annex Columnist, which is now part of Veolia since 1986. Dr. Philander is a main inventor of a number of processes frequently used in the pulp and paper industry, such as pure MBR, BAS, high BAS, and Lagoon Guard. So we're in for a lot of information from these two presenters. And with that, I'm going to hand it over to our first presenter, Rob Franken. Rob, are you with us today?
Yes, hello everyone. TJ, thank you for the introduction. Yes, I'm going to zoom in on our wastewater treatment technologies that we have and that we apply for pulp and paper mill wastewaters. We'll take you through some of the drivers for these projects. Obviously, we'll explain to you what these technologies are. We have a few case studies to present, and we'll also talk a little bit about when you can consider this type of treatment. And then we'll conclude with a Q&A session. So first about the wastewater characteristics. Of course, there are no one-size-fits-all solution for pulp and paper wastewaters. Actually, pulp and paper wastewaters are quite specific. And it's very important that we understand where the wastewater comes from, because that will tell us a lot about what we can do in terms of treatment. On this slide, you can see a few of those characteristics that play a role. Paper wastewaters are very different from pulping wastewaters, and sometimes there are integrated mills that do both. So all of these have their effects on the wastewater. Some important issues are, especially for pulping wastewater, are like toxicity. When you have different types of chemical pulping, there are residual CUDs or refractory CUD can arise in wastewater, and some of them can be toxic. So it is very important to understand all of that before you actually design your biological wastewater treatment plant. Another element that I will also show in the case study later on is like calcium. Calcium has a big effect on wastewater treatment designs. So especially in this type of industry, it is very important to understand that situation. And there are some other challenges like pH, flow variability, temperature. Those are more generic, and they can be designed for and should be designed for in the proper way. So what drives these projects? Of course, environmental compliance is a first major driver. You need to meet certain effluent conditions and criteria before you can discharge. So that will call for certain treatment technology. Another driver is just, if you're expanding your facilities and you have more wastewater, you need more capacity. That will drive projects. What we see nowadays, there are not so many greenfield projects these days, and especially in the United States, but we can see that many of the mills, especially paper mills, are going through a transition and converting their production. And this has an impact on the wastewater, either in terms of characteristics or in terms of load. And that calls for wastewater projects. And then the last one that I wanted to mention is that there's also a societal license to operate. You can think about carbon footprint goals or water footprint goals that clients impose by some corporate governance agenda, green agenda. Be a good neighbor to the society that we're in, and so you would really want to be good on those terms. So that also calls for wastewater projects. So, and we're going to zoom in a little bit on that conversion that I mentioned earlier. There are not so many greenfield sites, so the challenge that we see is how can we retrofit existing plants with either pre-treatment to get more capacity, or like post-treatment to get more efficiency or better performance out of these plants. So, and I already mentioned what the goal would be is get more capacity in these plants, get more efficiency, get more consistency, and get better performance. So before we zoom in on the anaerobic and aerobic technologies that we have to treat pulp and paper wastewater, let me just give you first a high-level overview of the difference between the two, for those of you who are less familiar with this. Each has its own strength and its weakness in a way. So let's go over this. So on anaerobic treatment is typically applied for wastewaters that are higher in COD concentrations. Aerobic treatment can be applied to also lower COD concentrations. So there's a niche for both of these technologies. Anaerobic treatment will typically very cost effectively remove bulk COD in a very compact plant and a very cost effective way. It will produce biogas, which is of course a renewable energy source, which will help to reduce carbon footprint in plants. And another important feature for anaerobic treatment is that minimal sludge is produced. So overall, it's a very low OPEX and CAPEX system. On the other hand, and this is where aerobic treatment comes in, if wastewater concentrations are lower, below a certain threshold, aerobic treatment is just a more logical approach to treatment. Also, anaerobic treatment will not remove any nutrients, and when nutrients need to be removed, like nitrogen, phosphorus, for example, then you need to have aerobic technology there. Also, if certain strict standards for these parameters need to be met, then anaerobic treatment would only be a pre-treatment, and aerobic would act as a post-treatment to meet those strict limits. Of course, aerobic needs energy for aeration. It will produce more sludge. So it really depends on the type of application where the selection for each technology is made, or sometimes a combination of technologies, depending on the scale and the size and the specificity of the project. So that's in a bird's eye view on the two different technologies. Now I will zoom in a little bit on the anaerobic treatment of pulp and paper wastewater. So there are different types of anaerobic treatment that can be applied in general for industrial wastewater. But as we've seen over the last few decades, pulp and paper wastewater really call for high rate granular sludge technology. We have two different types of technologies for this. One is the UASB system, which is a traditional granular anaerobic upflow system that has been developed in the 80s, and we have many of these systems running, in fact, for more than 3 decades in pulp and paper effluents. I will also zoom in on BioBed advanced EGSB technology, which is a more state-of-the-art technology that we use these days. It is generally speaking more compact and more cost-effective, and I will explain a little more in the next slide. So common to these 2 technologies is that they are granular sludge technologies, and on these pictures here you can see what that means. This granular sludge is a black caviar type of sludge, which contains the bacteria and the biomass that will actually convert the COD to biogas. When we start up systems, we introduce this for seeding, which will tremendously speed up the startup and will allow us to get a good performance from the start of the operation. So this is the UASB system, which contains this granular biomass that settles very well and sits on the bottom of this upflow system. So on this picture you see we take the wastewater and we distribute it on the floor of the reactor, and we get a good intimate contact of wastewater with this granular sludge. And when the water passes upward through this granular sludge bed, the conversions take place and the water gets treated and the gas is formed. So in the top of the reactor, you see those 3-phase separators, or settlers as we call them, to separate the gas from the water and the biomass, because obviously the biomass has to stay inside the reactor and perform the reaction. The water and the gas has to live separately on the top. The next slide shows the EGSB system, which is same in terms of biology, but it has a different configuration. It's a more slender type reactor, more vertical type. It is more compact, and you can see on that picture what it looks like. Same philosophy: you distribute water on the reactor floor, and in the top we have those 3-phase separators that secure the good distribution, good separation of sludge and the biomass, the water and the gas. And this is a typical design that Veolia has developed and that we have been using for the last decade, and also in many pulp and paper applications. The next slide shows what these systems look like in your industry. Those can be pretty good size. I mean, we have done paper plants with 100 tons of COD per day. These reactors can take different shapes and forms. The bottom left corner, you can see systems that we've done in concrete and civil construction. That is like in China, where that kind of construction is cost effective. Here in the US, typically all the systems are stainless steel, welded steel tanks or bolted steel tanks, depending on the client specifications. You also see a few snapshots of these internals. Yeah. So the big advantage of anaerobic treatment as a pre-treatment step is that you have a relatively compact and cost-effective way to shave off the bulk COD. Removal efficiency depends really on the type of effluent that we're treating, but can be anywhere between 70 and 95%. The system is characterized by very low operating costs because there's basically only pumping of water. There's nothing else. There are no moving parts. There is no mechanical mixing. So it's all very user-friendly and low operating costs, as I said, because also the sludge production, because of the nature of anaerobic treatment, is very low. Also, therefore, very low nutrient requirements for sludge growth. And as I mentioned earlier, obviously, producing biogas is a big bonus because the biogas can be used in the factory in boilers typically to get the energy back. So at this point, I would like to introduce Thomas, as he will be explaining to you the aerobic technologies that we have.
Thanks, Rob, and hello, everybody. We're then going to look a little bit into some modern aerobic technology for use in the pulp and paper industry. If you look today, the great majority of the treatment process in the pulp and paper industry will be aerobic, and then we are looking into conventional systems such as aerobic stabilization basins with huge retention time, very big volumes, or you have conventional activated sludge plants such as the one you see in this slide here, where you have aeration basin followed by clarifiers to separate sludge and put it back to the aeration basin again. What these technologies have in common is that the biomass you use will be in suspension freely in the water phase, and then you separate after the aeration basin and put back in a conventional activated sludge system. Today we have more modern technologies based on other principles, like you see next slide. Yeah, and then we're talking biofilm-based technology, which means that instead of having freely suspended biomass, you have biomass that grows on some kind of support or carrier material in your aeration basin. And one such very successful technology that's been around now for 25 years about, and the growing number in pulp and paper industry is the MBBR, the moving bed biofilm reactor. It's a single pass system, so water comes in and water goes out, and you don't typically recycle anything, but you go from this MBBR reactor into some separation. And in this case, the suspended material you have coming out from the basin will be the excess biomass and not all the biomass as you have in activated sludge. It means that you have much lower concentrations to deal with, and you can use many different types of separation like flotation, filters, active flow, and so on. So you can use very compact separation together with this in itself very compact biological technology. We are typically using very maintenance-free equipment. So if you look at the internals here in the tank, we'll have the key things will be the aeration grid in the bottom, which is done as a medium bubble aeration system in stainless steel. It's been around for maybe 30 years in the tank, 25 years at least, and without any maintenance. You have sieves on the outlet, as you see up to the left. This is to keep the carrier media in. So the water goes out, suspended solids go out, but the carriers with the biofilm on it will stay in the tank. Tank could be existing tankage or new tankage in concrete or steel or so. The biomedia, of course, is a key part of this process. We look more into it. We produce in the US today some of these media. We can have a look at the next slide. So this is the Anox K5 media. So you see to the left without any biofilm before you put it into operation, and then after a few days it will look like it looks to the right there with a biofilm growth on it. So it's designed to give you a very high effective surface area, because it's not the biomass amount that's important in the biofilm system, it's the surface area that is exposed to the water phase. Next. This type of technology requires a very little footprint. This is not a pulp and paper installation, but it just shows you that you have here a lagoon system treating wastewater, and in this case this little square with the 4 MBBR reactors was put in as a post-treatment to nitrify the water that could not be nitrified in the lagoons itself. And if you would translate this into kind of a, say, a BOD removal system, you would need about this lagoon volume you see here to do the same job as you would do if you go directly into this MBBR system instead. So it's very compact compared to the conventional systems. It's very flexible. So I will say that MBBR is a technology, it's not a process. And then you put this technology into the work and you make a process out of it, which could be like in the first case you see here, we say pure MBBR. So you have only MBBR reactors. which could be one reactor in some applications, or two, or it could be many, depending on the complexity of the treatment, what you need to achieve and what the wastewater is like. But you can also have this as a pre-treatment. This is very popular in pulp and paper. We call this total system a BAS, biofilm activated sludge. So we use a small MBBR reactor as a pre-treatment, and then going into activated sludge then can then be made much, much smaller than conventional activated sludge, and also get more stability out of this system. So you'll find them many, many places, this BAS combination. Then we have hybrid, which is useful. It's a lot of application in municipal. There are some in pulp and paper, and this is when you enhance your activated sludge process by having carrier media also in your aeration basin to maybe degrade complex, difficult compounds that will require very long solids retention time and so on. And you can also put MBBR as a post-treatment. In this case, you see here it's like post-treatment after activated sludge, but maybe even more common would be to have it, as Rob talked about, the combination of anaerobic treatment, aerobic treatment. This could be you can have an anaerobic pre-treatment and follow with MBBR as a post-treatment after that. So there are many, many different combinations we could do. One advantage is that we could actually design for future capacity increase. This picture is actually from such a case. It was in New Zealand many, many years back. We built the tank a little bit bigger than needed for the situation at that time, to leave it for higher capacity later on. So we filled only 30% of this volume with carriers, and then it could be increased to say 60% with carriers, and some years later when it was needed. I didn't mention before that, but the MBBR, of course, the carriers are moving around all the time, which is the key of it. And you can't fill 100% of carriers into your tank because then it won't move. So typically maximum fill is around 2/3 of the tank. And then you still have a very good movement of the carriers, which may avoid clogging of carriers, clogging of the bed, and you allow suspended solids to pass through the system without interfering with the carriers. What we can say about from the experience we have now for more than 25 years of operation in this industry, it's a very simple and robust technology. We are not depending on sludge recycle and the sludge settling quality, which is often a pain in activated sludge, that you have to follow and control the sludge settling quality to have the performance of the system. The carriers are moving, colliding with each other, and then cleaning them each other, and the excess biomass will leave the tank, and you separate it after the tank then to have a clean water going out. Experience is that the biofilm-based systems, such as MBBR, are much less sensitive to toxic shocks. So you can have spills and things, and it will take it well or recover very quickly. One special advantage could be that you can really operate at high temperatures. We have some thermophilic systems that are running continuously at, say, 55 or 60 degrees centigrade, up to 140 degrees Fahrenheit then, which would not be possible with conventional systems. And we can work at high and varying chloride concentrations and so on. And nutrient removal is possible. In pulp and paper industry, we normally have less nutrients in the water than we need for the biological system. But still, when adding the nutrients you need, it's very important to have a control so you don't have too much going out, because we see the strict regulations now coming in many, many places. In Sweden, we need to be sometimes below 0.15 milligrams per liter phosphorus, for example, and maybe 4 milligrams per liter nitrogen. So even if they're not high concentrations from the beginning, we need to be careful with what we're dosing, and we can control that very well with this type of technology. Next. So reliability, robustness is a great advantage. Small footprints, and as we saw, flexible configurations we can use in many different ways. Often using existing volumes or combining with other existing technologies to make a good fit. Simple operation, so you can focus more on the operation of your production than the wastewater treatment plant. Yeah. Yeah, and by that I would like to give the word back to Rob that will go into some case studies here.
Thank you, Thomas. Okay, so I already mentioned, I think we have a lot of references in pulp and paper wastewater. Overall, we have something like 600 reference projects worldwide when it comes to high rate anaerobic treatment with granular sludge systems. About 70 of those are in pulp and paper industry, and I just wanted to highlight one of them, or two. I have two of them here. This is a project that we have done in Germany, where the paper mill was actually, they shut down one of their paper machines that was doing graphic paper, and replaced that with a paper machine that will do the test liner and fluting for fluting production, so for cardboard. This had a big impact on the wastewater, as I explained earlier, so that called for a wastewater treatment project. On the next slide, you see that this system has sort of doubled in hydraulic capacity after the upgrade, and sort of tripled in the COD removal capacity. So this is a client where we have worked for 25 years. So initially we had a UASB system on site, and after they did their conversion, we upgraded the whole facility with a BioBed EGSB process. And on the pictures on the left-hand side, you can see those are stainless steel reactors. In this case, the biogas is also treated to get to a quality for use. So this was and the system is then followed by an activated sludge. As in this case, there's no MBBR, but there's a conventional activated sludge system. The second case study that I wanted to present is also on a recycled paper mill, where calcium is an important design factor. I already explained earlier that calcium has a big impact, especially on anaerobic treatment. Calcium tends to precipitate because of carbonate that's formed in the biological process, the CO2 that's produced. So calcium carbonate tends to precipitate and produce a high, heavy sludge. There was an existing anaerobic system on the site, and that failed. If you go to the next slide, that failed due to the fact that it completely plugged up the whole system. So what we did here, we introduced the BioBed EGSB process to treat the wastewater, but in order to handle those high calcium levels, we developed a high-loaded activated sludge system to precipitate out, basically to precipitate out any of calcium carbonate out of anaerobic effluent, and by recycling the calcium free, or I shouldn't say calcium free, but low calcium effluent back to the inlet. And by doing that, we can actually manage the calcium inventory and the calcium buildup in the system. So this is a typical paper application where calcium has such an impact, and where you really need to look at an integrated approach to facilitate anaerobic treatment for this type of effluent. So this is a plant that's treating about 13 tons, metric tons, I should say, of COD per day. And the typical value that we see is 80% COD removal. So in this case, as I mentioned, this is also like a pre-treatment. The next case study will be back to Thomas for an MBBR plant.
Yeah, thank you. We've chosen a couple of case studies just to demonstrate typical applications of MBBR in the pulp and paper industry. And this case then in Chile was like a mill increasing capacity of their production a lot, up to more than 1 million metric tons per year. And by doing that, needed to expand and to meet the regulations, and that's for COD, BUD, TSS, and so on, phosphorus. And the choice here, next slide, please. Hello. Can you hear me?
Yeah, we hear you, Thomas.
Oh, there it comes. Sorry, I can see it. Sorry. Yeah, the choice here was to install then a BAS plant. This was a greenfield installation then, so the whole BAS plant was built. Very often you may have like upgrade to BAS by installing MBBR prior to activated sludge to achieve the same thing. So in this case, for 120,000 cubic meters a day wastewater, this BAS plant was installed to remove maximum COD, which is about 80% of the COD, more or less complete BOD removal, and then a low discharge of total suspended solids. In this case, the phosphorus limit was like 2 milligrams per liter, which is high. I mean, we were far below that, and also nitrogen rather low out from it. So this is a very typical BAS installation in pulp and paper industry, some built as the new plants and some as upgrades when you go in with MBBR then to upgrade existing activated sludge. The other one, maybe not very typical production because it's a little bit special. It's a grease-proof paper, but just to show how we can use this technology in a very flexible way. And this mill needed then to meet discharge requirements that required biological treatment. And then we looked into the situation, and they had rather big clarification basins. So part of that was rebuilt into MBBR reactors to treat all their wastewaters biologically, and then use part of the clarifiers for separation after MBBR. You can see the next slide. And here we choose because one of the streams from a paper mill is the water flow rather high, but the concentration of COD low, while the pulp mill effluent is more concentrated and more complex because there were more complex things you need to remove. So in that case, 3 stages in series of MBBR, but it's straight through, flow through. It's just coming in, going from the first to the second, and second to the third reactor, and then to the final clarification. While the paper mill needed only 1 reactor before going to final clarification. And this was to remove almost all BOD then. Some of the EDTA, which is more slowly biodegradable compound, and about 50% COD reduction. So by this, the mill has met now their discharge limit for a long time. So Rob, I guess it's your slide.
Yep. So let's talk a little bit about when you can consider to do a treatment project, or maybe another way of saying is when you can contact us and talk to us. So basically, if you have a wastewater treatment plant there, and I'm assuming most of you in the industry already has wastewater treatment plants, so it is about how are we going to expand or enhance the treatment. So some of the factors to consider, if you're paying high sewer surcharges, have high operating costs for the treatment, this is can be a driver for you to consider upgrading of a facility. Obviously, if you have troubles meeting the compliance standards, getting notice of violations, that is a trigger to talk about wastewater treatment. Could also be that the municipality or the regulator is imposing new limits, for instance, with permit renewals on other parameters that you're not currently dealing with. That is definitely a driver for a project to see how you can enhance or upgrade the facility. And obviously, I mean, like many of you do now, converting production expansion or conversion of paper machines, getting different wastewater characteristics that may require also enhancing or upgrading of wastewater treatment facilities. Last but not least, for this slide, I wanted to mention that as Veolia, we also operate like more than 20 biological wastewater treatment facilities in the pulp and paper industry. So we have also a lot of operating experience that we can share with our clients. So if there are issues with stability, consistency of operation, there is definitely also an angle that we can introduce or help our clients. The next slide. So, what should be the steps to take when you have a situation like that and you need to think about enhancing or upgrading? I think it is important that when you talk to us, that we get a good understanding of what the drivers of such projects are, so that we can really understand the goals and what needs to be accomplished. And usually, very often, then we have to dive a little deeper into the wastewater treatment plant that exists already. So we regularly do like audits of existing facilities to see how it's actually performing in view of the incoming wastewater and the treatment objectives. And that can involve like sampling programs, monitoring program, assist the operator to see how the plant is functioning over time, trying to get an understanding of the operating cost of the facility and see how that can be improved. And that should give us a fuller picture of what can be accomplished with an upgrade of a plant, and make a very targeted proposal for that. Now, in an effort for us to get in touch with you in a more intimate fashion, to understand better your situation, and to get something to talk about, to get something going, what we would like to offer is to do a free biodegradability testing of your wastewater. So for a limited time, we will accept to do, if you send us samples to our laboratory in Philadelphia, we can do, for instance, a biodegradability test to see how it can be treated anaerobically, or what kind of performance you would get out of an MBBR plant, for instance. So we would definitely need to do that. Alternatively, what we can also offer to do is to do like a site audit, and do an assessment of an existing wastewater treatment plant, and review how that can be upgraded in terms of objectives that you may have for the plant in terms of capacity or performance. So if you are interested in this, I suggest you contact the moderator, TJ Willits, and his details are given in the slide below, and I'm sure you have it. So with that, I would like to hand the mic back to TJ.
Great, thank you, Rob, and also thank you to Thomas for sharing all of that information about those two technologies. We're going to transition now to our question and answer session. We have a few minutes left to take a couple questions. We had a couple come in already. Also, just a reminder, if you want to ask a question, there's a panel on the right-hand side of your screen. Go ahead and type that question in there, and we'll try to get to as many as possible. Also, while you're typing in that question, I just want to remind you that we're going to have our second webinar episode for this series for Pulp and Paper, and it's going to be on optimizing kraft pulping and recovery cycle operations with our specialty evaporation technology. And to go ahead and register for that, there's a short link there where that green arrow is pointed, and I'm sure everyone will receive an invite very shortly as well to remind them to go ahead and register for that. Okay, we have a couple questions coming in here. The first question we have is related to pre-treatment before the MBBR. So I guess this question is for Thomas. Thomas, what kind of pre-treatment is typical before sending that water to the MBBR process?
Yeah, what the need you have is basically some coarse screening to take out things that are bigger than the holes in the sieves in the MBBR. So very often we operate without primary clarification, because the primary solids we can allow to pass through the MBBR and separate together with biosludge after it. So depends very much on the situation, but we have no big need for a very, very careful pre-treatment, but some screening is needed.
Okay. Another question, this question is going to be for Rob. It's related to the high rate anaerobic systems. But the question that came in is related to the role or the effect that calcium plays within that system. Can you talk a little bit how calcium affects a granular sludge system? And you also mentioned that controlling the calcium concentration is important. And with that, is it better to do before as a pre-treatment or during the process? And I guess really, what is the most efficient way to make sure the calcium is held at bay within a system? Rob.
Okay. So during the conversion of COD to biogas, you will also produce CO2 because biogas is composed out of methane and CO2 predominantly. Well, the CO2 will be in equilibrium with water to form bicarbonate, and calcium and bicarbonate at a pH of 7 or 7.5 will form calcium carbonate. So in an anaerobic environment, there is always a risk of scaling when calcium concentrations are higher than 300, 400, 500 ppm in the incoming wastewater. So, and typically paper mills can have higher concentrations than that. So if you wouldn't do anything, then what you can see is that the calcium carbonate will precipitate in this granular sludge. The sludge will become very heavy and it will sit at the bottom, and it will be very difficult to mix it with the incoming wastewater. You will start a whole train of effects with short circuiting of wastewater through the bed, and the whole performance will of course deteriorate over time when your system is filling up with inert calcium carbonate basically. So that is a situation that you should prevent at all times, because if that fails, and that was the case study that I presented, then you really have to take down the reactor and replace it or clean it out. So for all the designs that we've done over the last decade is where there's two ways of dealing with it. Sometimes the paper mill itself can control calcium discharge to the effluent. So in that case, we just impose a limit on what we can take at the inlet of the anaerobic treatment. If that is not possible, then what we do is we introduce an internal recirculation. So we introduce a calcium removal step, and that is typically done on the effluent of the anaerobic reactor. And then after the removal of calcium, we take the low calcium effluent from that stage, and we bring it back to the inlet in order to dilute the calcium in the inlet. Because calcium carbonate will only precipitate above certain threshold levels. So as long as you stay below the threshold level, you can operate the system, and the calcium carbonate will not precipitate out to the extent that it will cause an issue or a problem. So it's a little bit complicated answer, I guess, but if someone is interested in this specific issue, I would be most happy to elaborate offline.
Great, thanks for that, Rob. The next question we have has to do with loading, really the max loading threshold for an MBBR. Can you talk a little bit about that, Thomas, of what sort of that top limit would be?
And it depends on what you need to achieve, actually. The advantage is that you can load it very, very high, but of course, in the end, the removal percentage is not very high. I mean, we have been up to like 50 or 100 kilograms of COD per cubic meter a day, but then you maybe have 20% removal, but it can still operate. Typically for pre-treatment, depending on the type of wastewater, you're somewhere between 10 and 30 kilograms of COD per cubic meter a day. If you need to have a complete treatment with MBBR, of course, you're much lower, maybe 3 or 4 kilograms. Now I'm talking kilograms of COD per cubic meter a day. It's just a simple way of describing it. But of course, it depends on how much carrier media, what surface area we provide, and so on. But just as a rule of thumb, you may say that somewhere there.
Okay, and just we have another questions. Basically, what do you do after the biological treatment to ensure that strict TSS limits are achieved? Is there a preferred technology for strict TSS limits? And I guess I'll hand that to Rob.
So if it is, it depends on what the limit is that we need to reach and what type of treatment that we have. If it is pure anaerobic treatment, and after anaerobic treatment, we will still have a TSS level left. But it is not common to remove that, because if you have only anaerobic treatment, it would usually be fit to discharge to a sewer. If you have to go and reach much tighter limits, then we would need to have the MBBR process as a post-treatment or as a full treatment if we don't have anaerobic pre-treatment, and then we would have TSS removal after the MBBR. Now there are several ways to do that. One way we typically use is dissolved air flotation, for instance, but we can also use clarifiers to separate out solids. If the limit is very tight, then we can actually follow that with like disc filter filtration, for instance, or sand filter filtration to reach limits of like less than 10 ppm, less than 5 ppm. It all depends on what the limit is, and then we should tailor the specific technology to accomplish that goal.
Okay, just another question. Let me make sure answers. If internal recirculation is done, so this is related to the MBBR. There's two constraints. The first is Legionella growth, and then the second is a chain reaction and calcium precipitation in the pumps. Do you have experience with this?
Yes, we've been working with it, and let's say this Legionella, of course, has been a big thing in Scandinavia for quite a few years now. Not that we've seen so much problem from it, but when you analyze Legionella, you find it in many treatment plants. And what we have done in some cases when you really wanted to avoid it was to operate the MBBR thermophilically, because then you will kill Legionella. We have one plant where we have a two-stage MBBR. We had the first one thermophilic and that was done to keep Legionella low or none. And then it's a mesophilic, lower temperature, second stage, to degrade some difficult compounds that would be difficult to get rid of in a thermophilic state. So of course it's something we're looking at. Calcium and MBBR is not, you're talking about pumps, but if we have high calcium levels in the wastewater, we are very careful with MBBR, because if you get precipitation on the carriers, they will stop moving. So we are very careful in the products to look through what kind of calcium specification there is. We have some carriers that are less sensitive to it, but still we need to avoid very high calcium levels in the wastewater. Then we shouldn't go for this, I say.
Okay. And with that, we have, let's get to one more question here. And it says, are the carriers tolerable to UV rays?
Yeah, they are tolerable in the application here. But of course, if you would leave them under the sun for a long time, not in water, that's why we have them in black bags and so on. So sometimes they've been stored in tropical countries for some time, in bags that will not allow UV to destroy them. But in the water phase, we've never seen a problem with UV, even in tropical countries. So it's a matter of how you handle them, how you store them, I would say.
Okay, and I just got one final question here. We're about at the end of our time. Is the anaerobic system produces biogas as a byproduct, methane. What is normally used? What do pulp and paper companies normally use this methane for?
Yeah, so I mean, the easiest way to use the gas is just to send it to the boilers. This is what most of our clients do. Of course, sulfate is often present in wastewater, and sulfate will reduce in anaerobic environment to sulfide, and part of that will end up in the biogas. So it is often we need to clean the gas before we send it to boilers. We have also technology, a biological technology for that. We call it sulfophane. It is also a biological process where sulfide is reduced to elemental sulfur, and that is then taken out of the gas, and so then we have a cleaned gas that can easily be used in boilers that are either retrofitted for the purpose, or the gas is just mixed in with bulk gas, depending on what the paper factory actually does in their boiler. So that's the most common way to use the gas.
Okay, well, thank you, Rob, and also thank you, Thomas. We're a few minutes over our time with some of those questions, but I hope everyone found that this webinar was valuable. Just a reminder to make sure you sign up for the next series if it's something that you're interested in on our evaporation optimization technologies. And lastly, if you just remember to take the survey after today's presentation, we'll use that feedback to make these presentations a little bit better. So again, thank you everyone for your time, and thank you, Thomas, and thank you to Rob for sharing all of that insight. Have a great day.